This is Algebra 2 with Trig, 6C.3. We're going to solve logarithmic equations. A logarithmic equation is one that involves logarithms with variable expressions. That is what these look like down here. A logarithm with a variable in the expression. The logarithm of a negative number or of 0 is undefined. So what that means is you can't take the logarithm, the log of negative 8, because 2, even of base 2, 2 to no power equals negative 8. You could even try that in the calculator. When you do alpha y equals, you can go over to your change of base, and you can plug in your negative 8, and we should get an error. 2 to no power equals negative 8. 2 to the first power, of course, equals 2. 2 to the 0 power equals 1. 2 to the half power equals the square root of 2, and so forth, but you're never going to get a 0 value. You'll never get a negative answer. So that's why that is undefined. So to check for extraneous solutions, we've got to check that our argument, if our argument is less than or equal to 0. The part that's inside the equation, the expression, when we plug our x in, the question is that going to be negative or is that going to be 0? If that happens, then that solution is extraneous. We have two different types of equations that can come involved here. If you have two logarithms that equal each other with the same base, that's the type that we're doing now. If the base is the same and the x and y are the same, then your x is going to equal the y. If they're all positive numbers and we have this as our equation, then the x and the y have to equal each other. So with numbers, if log base 2 of x equals log base 2 of 7, then the x has to equal 7. And if x equals 7, then you can do a log of it, any log that you want, or any natural log that you want, and you can still solve out what that needs to be. So let's try some of these. Notice that we have an equal sign. We have a log on both sides. Natural log is just a logarithm with a base of e. They both have the same base. So we're going to set our two expressions equal to each other and solve for x. So we add 4 to get to 15, divide by 5, which gives us 3. So we have this answer of 3. If we plug the 3 in here, 7 times 3 is 21. 21 minus 4 is 17. If we plug the 3 in here, we get 6 plus 11 is 17. Those are not negative numbers. Those are not 0. So that should be okay. It should work just fine. And since they're both 17, natural log of 17 equals the natural log of 17. Works out great. Here we have two logarithms with the same base. So we can set our expressions equal to each other. And then we just use our algebra skills to solve for x. We divide by 3 to get to 4. So when you plug 4 in, we have 4 times 4 is 16. 16 minus 7 is 9. Plug 4 in and we get 9. So notice we did not get a negative answer. We did not get a 0. So that works out great. Okay, case number 2. Our second case. If we do not have the situation up top, if we do not have two logarithms that equal each other, like over here, we have a logarithm that equals a constant value. We only have one logarithm. We're going to have to condense or simplify to make one logarithm. Then we're going to rewrite the logarithm in exponential form so we can solve it. We've got to watch out for extraneous solutions. So, of course, the constants are going to come together, and we'll have log base 5 of 3x minus 8. That equals 2. Now, notice the logarithm equals an integer. We don't need to be solving for an integer. The variable is not for the exponent. So we need a logarithm to solve if we have equals some sort of an x. We don't have that. So we can switch this back to exponential form. We know what 5 squared is. We would add the 8 to the other side to get 33 and divide by 3. So x equals 11. When x equals 11, we can plug it back in. 33 minus 8 is not a negative answer. So we do not have an extraneous answer. Here we come with a different one. This is interesting. This has two logarithms on the same side of the equal sign. They're separated with an addition. So what are we going to do? If you're adding two logarithms, we can condense them together by taking the log of 5x times x minus 1. We condense the two logarithms into one logarithm. Because this is a common log, we know the base is 10, and we can write this as 10 squared equals 5x squared minus 5x. We distribute that through. Then you can subtract your 100, because that's what 10 squared is. We have 5x squared minus 5x minus 100. And we can factor that. It might be easier to divide everything by 5. We get 0 equals x squared minus x minus 20. We have 4 and 5, a negative 5 and a positive 4. So the zero product property gives us two answers. Now we take those answers and we plug them back into the original equation. When you plug 5 in, you get 5 times 5 is 25. Well, you can do that. It's not a 0 or a negative. 5 minus 1 is still a positive answer. Negative 4 times 5 is a negative answer. So that immediately removes that as a possible answer. This is an extraneous solution. We put a light X through the answer, and we circle our real solution. when you plug 5 in, 5 gives you 25, 5 gives you 4, so we're all set. We look at our next one. We have two logarithms with a plus in between. That tells us we are going to multiply our two expressions together. We condensed it. So we're going to say 6 to the first power equals 2 minus x. And 3 plus x. So we would need to FOIL that together. That would be 6 equals 6 plus 2x minus 3x minus an x squared. Notice that we have this x squared. This x squared is negative. We would want to bring the negative x squared over to the positive side. So we add it over. This becomes negative 1, so we need to add an x to this other side. And the 6 would need to come over as well. So we crossed everything off on one side. We got 0 on one side. So we can factor that apart as x and x plus 1, and we can use the zero product property to help us figure out our two solutions. Now when we take these two answers, I plug my answer in and I get 2 minus a negative 1. 2 minus a negative 1 is actually 2 plus 1, which is 3. And 3 plus a negative 1 gives me 2. Neither of those are 0, neither of those are negative. And the same thing for 0. So those are both solutions to our equation. On the flip side, this is you try. So you go ahead, work through these, pause the video, work through them, come back and check out your answers. So since we're adding two logarithms together, we write it as one. This is called condensing. I like to write the x in front of the binomial. So then we're going to write it as 6 squared equals x squared minus 9x. We'd subtract over 6 squared, which is 36. And that can be factored apart using 12 and 3. So it have to be a negative 12 and a positive 3. And we can use the zero product property. And when we plug in a negative to the original equation, you would get a negative answer. You get a negative value that you're taking the log of, and that's undefined. So this is an extraneous solution. Not because the number is negative, but because when you plug it in, you get a negative. Here we have two logarithms that equal each other, so we can just set our two expressions equal to each other. So we're just solving our equations. 20 and 10 is 30. When you divide by 5, you get 6, and when we plug 6 in, we get 2 positive results. Then we have our situation when we have a single logarithm. There's nothing to add or subtract, but we can divide by 3. So that's log base 7 of 3x minus 2 equals 6 divided by 3, which is 2. I don't need a logarithm if it doesn't equal some sort of x. So 7 squared equals 3x minus 2. That's 49 equals 3x minus 2. Add the 2 across gives us 51. And when we divide by 3, we get 17. Plug 17 in here and you get a real value greater than 0. So these are additional practice problems. So just as a reminder of how this works, you can either pause it, work those out, then come back and check it out. There'd be a great option for you. 2 logarithms that equal each other. We are going to equal our expressions equal to each other. Subtract over to get 7x. Subtract over to get negative 14. Divide by 7. We got negative 2. Now notice, here's an answer of negative 2. We typically would say that that's going to give us an extraneous. But when you plug it in here, you get negative 2 plus 3 is 1. That's okay. Plug in a negative 2 here, you get negative 16 plus 17 is 1. So that's okay to have. So x equals negative 2 is your answer. Here's 5 squared equals x minus 4. 25 equals x minus 4. Add the x over, or add the 4 over, and you get 29 equals x. Number 3 looks a bit tricky. Trying to recognize what you should move and how it's related. You would not treat this as 1 minus 2, because the 2 is times in something. So we would need to subtract the 1 across. And then we'd have to divide by the 2. And that's equaling a positive number. So e to the 5 halves equals x. And if we wanted the decimal version of that exact answer, we could say e to the 5 divided by 2, which is 12.18. On this side, we're adding 2 logarithms together. If you're adding 2 logarithms, we want to condense those first. Then we would write it in exponential form. Subtract over the 36 and factor it apart. That looks like 9 and 4. A positive 9 and a negative 4 would add together to be 5, but multiply together to be 36. Specifically, a negative 36. When you plug in a negative 9, you get a negative answer, so that's going to be extraneous. You plug in a 4 and you're okay. We need to condense our 2 together. So that gives us 4 squared equals x squared minus 6x. We'll subtract our 16 across. That looks like 8 and 2. 8 and 2 are 6 apart. So negative 8 and a positive 2. So that gives us 8, and that gives us negative 2. The negative 2 would be extraneous. So 8 would be our only answer. And we can finish up by adding 2 across. So that's e to the 10th power equals x plus 3. E to the 10th power, 22,026. And we subtract 3 from that. We have to subtract 3 from that, which gives us 3 less. And that's our crazy answer, 22,023.47. So our final question is to create a logarithmic equation that has no solution. There's a couple different situations that we could go through. One that I was thinking about was using a logarithm. ln is just as easy as anything. If you use x plus a number and equal that to the same base logarithm, of course, if we use x both times with a different constant number, doesn't really matter what you use, to solve it, when we set our two expressions equal to each other, every time we do this, the x's are going to cross out completely. So we will get a false statement that says 2 equals 4. There is no solution. This logarithm never crosses that logarithm, so there's no solution.